Building a real-time chat application looks simple on the surface. You type a message, and it appears on your friend's screen instantly. But maintaining that illusion of zero latency across millions of active users requires solving one of the most difficult challenges in distributed system design. Most web infrastructure is built on the standard HTTP request and response model. When you log in or update your profile, your app makes a quick stateless request to a server, gets an answer, and hangs up. But chat traffic can't wait for the client to ask for new messages. This diagram illustrates the architectural divide. On the top, you have traditional stateless services sitting behind a load balancer. On the bottom is the stateful chat service. To achieve low latency messaging, the client establishes a WebSocket connection, a persistent bidirectional protocol that stays open, allowing the server to push data to the device the exact millisecond a message arrives. To a junior engineer, this stateful block looks like a straightforward solution. You open a continuous pipe between user 1 and the chat server, and another pipe to user 2. It feels like a direct, unbroken wire connecting two phones. But relying on an unbroken wire assumes perfect conditions. In reality, mobile networks drop packets, users walk into elevators, and servers experience sudden hardware faults. If your architecture relies entirely on routing messages through active, in-memory connections, a single failing machine takes the data down with it. Any message held in transit when that server goes dark is permanently lost. To prevent data loss, we have to abandon the idea of a simple pipe. A resilient chat system requires a massive, asynchronous, fault-tolerant database architecture working behind the scenes. The first component to break at scale is the load balancer. Standard load balancers distribute traffic evenly by bouncing quick HTTP requests across a fleet of servers. But WebSocket connections stay open for hours. If a subset of servers reboots, thousands of clients will instantly reconnect. A naive load balancer will route those long-lived connections to whatever machine is next in line, quickly suffocating specific servers with traffic while others sit idle. This diagram shows our solution. We place service discovery in front. When a user logs in, API servers consult Zookeeper. It evaluates server load, selects the optimal server 2, and passes the IP back to the client to initiate the WebSocket. By separating the process of finding the right server from holding the connection, the system maintains a balanced load across the entire fleet. Once the connection is stable, user A can send a message intended for user B. The instinct is to have the chat server hold the message in memory and forward it directly, but if the server holding user B's connection crashes exactly at that moment, the undelivered message vanishes forever. To guarantee delivery, chat server 1 gets an ID from the generator, then drops the message into a sync queue that writes to a key value store. Safe on disk, the system forwards it to server 2 or a push notification server. The open WebSocket is an opportunistic delivery vehicle. It allows for fast transit when available, but the system doesn't depend on it for data integrity. Treating the delivery mechanism and the storage mechanism as completely independent systems ensures that a dropped connection never results in a dropped message. This decoupling also solves the issue of multi-device synchronization. A user might receive dozens of messages on their phone throughout the day and then open their offline laptop in the evening. If the central database had to track exactly which specific device rendered which specific message, the storage overhead and computation would paralyze the backend. Instead, edge devices carry the memory burden. Here, user A's phone and laptop each maintain a current max message ID. When processing a message, the device updates this tracker. Reconnecting, the laptop directly queries the key value store for messages with an ID higher than its local maximum. By using asynchronous edge pulling, the backend is entirely relieved of tracking individual device states. It just serves the data the clients ask for. Group chats introduce a different scaling problem. A single incoming payload now has to be delivered to multiple distinct users simultaneously. For small groups, we use fanout on write. This chart shows a message from user A copied into the message sync queues of users B and C. Duplicating messages into personal inboxes simplifies client syncing, letting them check a single source for updates. This works efficiently for groups of a few hundred members, but duplicating a single message reference for a channel with 100,000 users would instantly overwhelm the message queues and exhaust database capacity. System architecture relies on strict constraints. You build a push model for small groups and transition to a pull model where clients fetch from a shared channel for massive audiences. The scale dictates the design. This brings us to the online presence indicator. Storing a simple Boolean flag in a database that says a user is online is inherently untrustworthy. Mobile users rarely log out cleanly. They walk into tunnels or run out of battery, abruptly severing their connection without telling the server they've left. To accurately track presence, clients use this heartbeat mechanism, sending periodic pings to the server. If heartbeats arrive within a threshold, the user remains online. If a client goes silent past the 30-second timeout, the server intervenes and marks them offline. Once status changes, it must be broadcasted. These presence servers use a publish-subscribe model, publishing the update to channels subscribed by active friends. To prevent network storms for users with thousands of connections, the system must batch and throttle these broadcasts. An accurate online indicator is not a static data point. It is an active, continuous computation requiring constant validation between the client and the server. When you piece it all together, a modern chat application is a symphony of parallel components. API gateways, service discovery nodes, key value stores, sync queues, and presence servers all operate independently. If a chat server fails, the WebSocket snaps. Because delivery is decoupled from storage, messages remain safe in the database. The client asks Zookeeper for a new server, establishes a fresh connection, and pulls missing data using its local maximum ID. Because these systems are modular, operations teams can scale the database clusters during high-traffic events without touching the presence servers or the ID generators. The true triumph of distributed system design is abstracting all of this complexity away. You build massive, fault-tolerant, asynchronous machinery just to give the user the simple, uninterrupted illusion of a green dot and a chat bubble.